Well, so first of all, Alessandro, thank you very much. Thank you, all of you, for being here. The idea is to bring you to this liquid tunable microscopy, and I need all of you for growing within this concept, and you will see which is the meaning maybe at the end. My lab is split in two places: the Italian Institute of Technology, that is a multidisciplinary institute, and this part of the current group of PhD student and postdoc. And my roots are from Department of Physics, University of Genoa. I'm also there. And this is the very first group I worked with. Maybe you can recognize here Davide Mazza, Valentina Corsi, she's in Paris, Emiliano Rozziti is in Paris, Ilaria Testa in Stockholm, Giuseppe Vicidomini is back from the Stefanel lab and is in my group today with Francesca Cella and Paolo Bianchini. In my lab we also have a center that has been founded by Nikon, and is the Nikon Imaging Center. You are welcome to come for free, or if you want to pay a fee, you can do that. You're welcome. I'm from Genoa, please remember. And what you simply need to do is to book your microscope. So the microscope you need, we have more or less 12 optical setup in the Nikon Imaging Center. Within the activities of our group, there is something you will follow in these days with Marco, that is here, Simon Luca, and Takahiro will leave, but Takahiro was also setting up the system with Alessandro this night. A Genoa instrument. I like to say that with Genoa instrument, Genoa, because we are from Genoa, we have only one football team in our city, colors are red and blue, and this is the reason why I'm interested in visible light. Because visible light is from red and blue. Please remember, in Genoa, we have only one football team and one great company for in the future for microscopy, that is Genoa Instrument. The idea is to develop pret-à-porter super resolution microscope. This means that electronics, software, and ideas or how to put them together are from our lab, mainly from Marco, Giuseppe, and Simon Luca now, that is the last one joining the group. There is some electronics you can see here. And the best part of this device is the detector. I will be back on this later, and you will be able to appreciate what does it mean having this detector, that I will reveal later, only later. This is what you can see if you have a look inside. But yesterday they were very happy of being able to have this aligned. And so now you see that for the user, you have the sample holder, the objective, and a screen where you can see what you're doing. I will be back on some details on this instrument only later. Genoa instrument. Genoa is more than this. And please give me only 2 minutes to bring you to your attention the fact that recently we have this dramatic event in the city. So we have this bridge falling down. And this was the bridge connecting not only the city, east and west, but was only the bridge connecting IIT Morego lab with IIT Erzelli lab. And every day, going to the IIT, we were passing on this bridge or down this bridge. So I think that in Genoa, everybody living in Genoa could be a victim of this bridge any day of his life. So we survived. And in case you come to Genoa or you're traveling and you see a T-shirt with this kind of logo, this means that in case you buy it, you are helping the city in trying to restart, and 600 people that are without house now and are looking for an accommodation and relatives of the 43 victims that we had. So sorry for this, but just to remind what happened in our city. So let me be back now to our fluorescence microscopy school. The core for the liquid tunable microscope is what I like to call multi-messenger optical microscope. Multi-messenger because the idea is to shine light on a sample and to try to collect all signals sent back by the sample using photons, using light. Any kind of signal can be scattered, reflected, fluorescence, maybe in the future also phosphorescence, any kind of signal. To do this, let's say what I call the groundbreaking challenge is to build an instrument having everything inside. And you will see why in the next slide, in the last slide, I'm interested in this. This instrument is part of this project because it gives us the ability or the possibility of building all the modules that have to be shared by a user. During the story today, you will see light impinging the sample, a biological story that is one of the stories we are interested in, and some future developments using advances in artificial intelligence. Within this idea, this multi-messenger microscope, there is this maybe crazy idea that has been named liquidopy, liquid tunable microscopy, and we will discuss about this after discussing about the approaches that we have in our hands today. As most of you are interested, we are interested in traveling in the biological world using light, collecting this signal. And today, more specifically, I would like to focus our attention on the cell, but more than on the cell that you know very well. You know how intricate is the world inside this envelope here. You have your cell with a membrane, and within the cell you have another envelope with DNA, with all the information contained there, and with some motives, organizational motives, that are determining the fate of the cell and the way it's function, the way it is functioning in the body, our body. I'm interested in the way, in a specific temporal window of the life of the cell, that is the interface that most of you know very well, better than me, the way DNA is organized within the nucleus. So I'm interested in chromatin DNA. Now, this kind of scientific interest fits very well with the multi-messenger microscope and is a sort of, let's say, El Dorado for a microscopist, because today you have a sort of unique possibility of building, realizing, or having in your hands an instrument that allows you to follow what's going on at different level of spatial resolution. So you can really tune across details in your sample using the very same instrument. That is carved glass, piece of glass, so a lens, and visible light. So the idea is to be able to tune here. Why in this specific case? Because we are interested in the way chromatin is organized. In the years you had different models, different exotic models, including fractal possibilities in terms of organization, and different ways the chromatin compacts and contains the information related to DNA. On July 27, 2017, there was this paper published on Nature. I don't know many of you read this paper or noticed this paper. Apart from the cover, that's big interest for this topic, there are two aspects. One is that chromatin organization is revised. So Ellisman group and people involved in this research are thinking that the way chromatin is compacted in the nucleus is made by disordered 524 nanometer chains. The reason is because this allows chromatin to have time to change this kind of sliding door when it's releasing information coming from the DNA filament. But for this research, they used a very good approach that is a mix between light interaction, so inducing photobleaching in the sample, that is inducing oxidation of some element in the sample, that in this case become as a contrast for electron microscopy. So it's a very great chain, a sort of green fluorescent protein working for the electron microscope. It's great. For their preparation in the sample, they used fixation in glutaraldehyde. And so at the end of the article, they discuss about potential effect of this kind of fixation that produces crosslinks, that can produce some alpha and so on. And so in any case, they opened a new window on the studies of organization of chromatin. I'm interested in the dark regions that are inactive and in the gray regions that are more active, and to try to find a way for following changes in organization of chromatin, not only using, like in this case, fluorescence. So the idea is to be able to follow this aspect, dynamics, this aspect, and the way chromatin organization is linked to the cell fate. The optical microscope is perfect at this. In order to be more focused in terms of application, we're thinking to work on this kind of sample. Why? Not only for the disease itself, that probably you know as biologists, or you know from movies. There was a movie related to this that is completely false, because during this movie you see that the main actor becomes young again. The reason is to have Brad Pitt in the actor staff, otherwise this couldn't work. But we are interested in this not for Brad Pitt, but because the shape of the nucleus of most of the cell is a circular shape, and so chromatin can be organized in a certain way. But in this case, in case I'm able to use a word coming from Naples, it would be sgarruppato, so it's not exactly ordered, it's a little bit strange, but this could induce some constraint, mechanical constraint, in the organization of chromatin DNA. And this can affect the way the sliding doors can be opened or not. So for this reason, we are interested in this kind of story, including progeria. The first way for attacking this issue is related to the use of fluorescence. You had a very brilliant lesson about fluorescence this morning, so you know everything. I like just to show you one slide by David James. Why fluorescence? Well, because it's pretty. There's a very good reason. But the very good reasons are in the fact that when you have a fluorescent molecule bound to someone, you can also detect some changes in the neighbors that tell you something, not only in terms of intensity, of change of the intensity. So you shine light, you get fluorescence, and you are able to locate the molecule you are interested in. But you are also able to detect information about ions around, electric fields, viscosity, polarity of the system, pH, temperature. And now that we are in the era of single molecule microscopy, improvement in resolution, in spatial resolution, and we started to use more parameters related to fluorescence, so we can take advantage of this ability in order to have maps that are related with other aspects that are not only position of the fluorescent molecules. Then you heard about, and you know about green fluorescent proteins, so these guys, but what is, and they got the Nobel Prize years ago, 2008, But what was very inspiring when microscopists had this green fluorescent protein in their hand was what Jennifer Lippincott-Schwarz and George Patterson found. Was something that was known for wild type of green fluorescent protein, so that you could have some switching from an emission to another. If you were not using in an appropriate way green fluorescent protein, you could have a signal in the red, switch to the red. But they found that with some mutation in the protein, they could have a protein, fluorescent protein, that had the possibility to be photoactivated. What does it mean? It means that you shine light, you receive no signal, but if you shine another wavelength, more energy, you change the structure, you induce a decarboxylation in this case, you change the structure, so spectral response is different, absorption is different, and you can get a fluorescent signal back. This is great twice, because with a green fluorescent protein, you are able to have your fluorescent label expressed by the sample when you want, close to the molecule you are interested in, but now you can decide when you want to switch it on. And you can also decide in which region of the cell you want to focus your attention. And so, for example, in case this is the scaffold, you can induce switching on in regions within the cell or in the membrane or wherever you want, or you can detect by switching in an appropriate way green fluorescent proteins contained in the vesicle if they go to the membrane or not. So really you can design new experiments. Among these experiments, there are the experiments related with super resolved fluorescence microscopy, and we will see in a very few slides what's going on. So we have in our hands fluorescence. We can use fluorescence for performing, let's say, also deep imaging in the sample. You have seen before three-dimensional views. So you have so many tools in your hand using fluorescence that now you need only to push a little bit more on two aspects. Increasing your ability in following events with a better detail, and trying to get information from fluorescence behavior in your sample. And so if you have a look today to the approaches that you can have in your hands, you see that you have so many, really so many. But now you can use two categories, two main categories. One kind of approach is related to optics. So you can arrange optics, you can find solution in optics that can give you an improvement when you collect your signal, for example, under the aspect of spatial resolution. If you play this game, at the end you can be frustrated because you can push whatever you want, but for a reason that will be clear in a very short time, you cannot push more than 3, 4, 5, 6 times. You are limited at the end. But now you have another approach in your hand, that is the probes approach. The probes approach now reminds you immediately the fact that you are able to control switching on and off of fluorescent molecules. So you can control your probe in a very nice way. You can perform, and you can perform FRET, fluorescence correlation spectroscopy, FRAP, a lot of methods in the past that were like the F methods. But you can use this ability in controlling your probe for improving resolution, and you have the single molecule or individual molecule localization methods and the STED approach and other approaches in terms of improvement of resolution. Only after discovering this ability of controlling fluorescence in fluorescent molecules, in fluorescent probes. So now you simply have to try to start from a suitable setup. And there is one point that is very interesting. the way you shine light on your sample. You would like to be flexible in the way you do this. Simon Luca, for example, for his PhD thesis, developed a very good job and was able not only to work with this special lens that I will discuss with you in a few minutes, that is a liquid lens, but please keep in mind that liquid tunable microscopy is not related to the liquid lens. By chance, the name is liquid tunable microscopy and the lens is liquid. Simon Luca was able to mix the abilities, the properties of this lens with the properties of a classical lens to shape the investigation beam. That for some application can be useful when you want to go deep, or if you want to go fast, or if you want to go shine light in a certain way with a certain intensity distribution on your sample. So it's a good step, having the ability of manipulating the illumination beam. And the liquid lens, here you can see a drop of liquid, that is silicone oil, works in a very nice way. There is a drop of liquid, then you simply need to have some music, not audible music, so frequencies are from 140 kilohertz up to 9 megahertz if you want. You send this music to the drop of liquid. You induce some small changes in a molecular property that is called refractive index, so the time needed for light for passing through an object. You induce a very small change, and the objective that is immediately after your liquid lens with the series of lenses that are in the objective amplifies this small change. When you change the refractive index and you focus your beam on this object, the effect by changing this refractive index is that you change the focal region. And so you are able to change the focal position in a very fast way, 140 kilohertz, up to 9 megahertz if you want. This is interesting because you are able to change focus and continuously collecting information, maybe also in a redundant way, of an object, and you know by your signaling time the position of the photons that are impinging your detector at a certain time, because it's time giving you the position of the focus. If you play this game with a conventional confocal microscope, simply adding this liquid lens behind your objective, you plug it in a very simple way. You can, with a confocal, you can collect one plane, scanning, and then you move to another plane. With a liquid lens, while you're collecting this plane, you are collecting several other planes because you are changing focus so fast. Limitations, unfortunately, is only limited by signal-to-noise ratio. But could be good for a lot of applications. You can also use this game for producing another way of investigating the sample that is called plane of illumination, selective plane of illumination or light sheet. This means that instead of being lazy, like I am, and most of you in this room when working with a microscope, we are lazy because we shine light and we collect photons. We don't move. What about shining light, being more, a little bit more, not too much, athletics, and changing our position 90 degrees apart, and collecting photons coming from all the line that I illuminate. In this case, I'm removing background. So this is a very good way for removing background. Then I can try to move this plane of illumination, collecting information using a wide field microscope, conventional microscope, okay? Now, there is some inertia in doing this because you have to physically move your plane of illumination, and then you have to move an object, is a glass object in space. And we decided to, with Martillo Castello and some other, to build this fast inertia-free volumetric light sheet microscope. What does it mean? It means that we have a crystal for inducing the creation of the plane of illumination and moving this plane of illumination. So you shine light to the crystal and you have this. While this is moving in this way, without any triggering, I send through the liquid lens a very fast collection, changing focus point by point. And so I have no parts in motion, and I can collect everything that's going on in my sample in the 3D space. If I play this game, well, let me skip this, but if you're interested, we can be back then on this. So this is for the focusing, and this is for the creation of the light sheet. If you play this game and you have a lot of light, like in this case with reflecting particles, you can collect 200 volumes per second. That is a good number. When you go to real biological sample like this one that you can have for free from a small lake close to our lab, Paramecium, you are limited to 10 volumes per second, however, 300 frames per second. So it's not bad. And since you have in your hands this possibility of shaping the beam, of misaligning or realigning the beam and working with a liquid lens, you can use this displacement to follow in the three-dimensional space single molecules, like in this case. This is a quantum dot moving across the periphery of a cell, and you can detect with nanometric precision. So we have in our hands this possibility. So we can shape the beam, we can control the scanning, we can do everything. We have the green fluorescent protein, so we have a lot of tools in our hands. And now we are interested in resolution. I'm sure that you know everything about resolution, but just to be more sure, let's discuss a little bit what we mean. For sure, it is your ability in detecting 2 points when they are close one to the other at a certain distance d. So this is what you normally call resolution. And you have seen from Alessandro and from other the classical definition. This means that if you have changes of intensity in space, and these changes are very fast, so objects are very close, you can detect or not them within a certain limit. If these changes are less close one to the other, it's easier to detect them. Another way for describing what's going on for a signal like this is to perform or to think about another issue. When you listen music and you have your amplifier, sometimes your way of reasoning is not related to the space and to the waves in the space, but are related to frequencies, right? So you have high frequencies, low frequencies, mid frequencies that you can adjust in your amplifier. And they are related to a sharper signal or to a broader signal. You can play the very same game with space, doesn't matter. So with light and photons coming from your sample, you move to what is called Fourier space. So these are frequencies. High frequencies are related to objects that are very close one to the other. And when you move here, these are a signal that is flat, that does not change too much in space, okay? But cells, signals, you don't know which kind of information they bring to you, otherwise we don't perform any research. All frequencies are there. Your microscope is an instrument having a cutoff of frequency, like our ears, like some other devices. And so some information cannot enter in your system and cannot reach your detector. This is the cutoff frequency. Before moving to a concept related to super resolution, which are the criteria we have to define which is the current resolution of our microscope? This is an important point, because why are you using your microscope? Because you have an experiment. You prepare your sample, then you decide to form images, so to collect data in a form that is an imaging form image. And when you see this image, you try to understand, to speculate on what's going on, if your hypothesis is right or not. But it's very relevant that you can trust in the spatial resolution, because if spatial resolution is 1 micron or is 1 nanometer, your conclusion on the sample is different, okay? So you need a criterion to be sure that the resolution you have in your image is the resolution you can use for finding a conclusion for your research. And you have different criteria. Well, one can be using some model of the image formation system, and then with this model you can understand by the properties of the lens and the characteristic of the light, using a law that Abbe never wrote but is known as Abbe law, which is the spatial resolution you have in your lens. I will be back on this aspect related to Abbe. Or today you can use calibration sample, rulers, DNA origami. Now this is a technology you can buy. Only reminding you that this is not your sample, it's the ruler. It's related to your sample, can be related by the properties of fluorescence, by the aspects of imaging you're taking care of, but it's not your sample. Or you can do what all of us, what we do. We watch our image. Someone is very skilled, some other are less skilled, but you can find in your image a very good region. In this good region, you have a line profile. You check which is your ability in distinguishing lines or points that are very close one to the other, and your statement is, this is my resolution. Okay? All three cases are, this is related to a model that cannot take into account everything. This is related to a very nice calibration sample that is not your sample. And this is related to a measurement that is not the full sample. What we propose is to be back to this name Fourier, that is called Fourier-Ring-Correlation. That at the end is a very simple approach that I think you can manage and you can use in a very simple way. First of all, does not need any a priori information. So not a model, nothing, no knowledge about the sample. This approach takes into account all optical conditions. So the current optical condition you are working with, and is measured directly from the image of your sample. The only point you have to take care is that you need two identical, independent, statistically independent images of the same sample. Well, for some reason, using this instrument, you can get this in a very nice way. But using a conventional system is the same. You simply acquire two consecutive images in a very short time. You're able to do that. And if you have some movement in the sample, don't worry, because you are able, or the system is able to recognize this. There is, you can detect simply a resolution that is worse than the real case. But you are not detecting a resolution that appears to be better than the case you are facing. And so these are the two images. This is the very same signal in the frequency domain. Your computer that you have on board can perform this kind of cross correlation, so the Fourier-Ring correlation between these two signals, and you get at the end this curve here. This is the cutoff frequency, and this is the current resolution of your system, imaging system, related to the sample that you have in your hands. And for example, in such an intricate condition, you want to find some conclusion about distribution of chromatin here, you can speculate, you can conclude whatever you want, according to your experience, to your experiment, but what we can say that in this case, resolution you can trust with is 37 nanometers. Nothing more comes from this kind of approach. And you can do this not exactly for free because you need 2 images instead of 1. Now, if you're interested in resolution and super resolution now, I recommend, and if you cannot find this in your digital subscription, you can send me an email and I will be more than happy to send you this paper by Colin Shepard that is discussing about the concept of resolution and super resolution. What is nice in this paper is the discussion about the Abbe law, and because Abbe never wrote the formula that is on the monument and we call the Abbe law. However, reading the paper that is overcited in German, here you find part of translation in English, you can find some words that help you in writing a formula that is close to the one we know as Abbe law. The concepts are there, but he never wrote this. The experiment by Abbe was a completely different experiment. Abbe was not interested in finding the minimum distance you can detect 2 point-like sources. The experiment of Abbe was in coherent light, was with stripes, was in the frequency domain, and was not exactly related with what we have in mind when we read the Abbe law. However, and this paper is very interesting because it gives you a chance to understand better what's going on in terms of formation of the image. So now we are in this condition. You can have low spatial resolution, you can improve the resolution, and what I'm saying now is that with the super resolved methods, we have in our hands the possibility of turning a knob, getting a spatial resolution that is unlimited. There are no limits for the spatial resolution. You turn your knob and you move from the classical resolution, the fraction limited resolution, down to this point. And now you say unlimited, but here is not 0. It's 25, right? Because we are interested in working room temperature, living samples. From physics textbook, you remember that there is a quantity called kT, with K is the Boltzmann constant and T is temperature. And so when you are working at a temperature that is different from 0, you are inducing some motion in your sample, you induce some energy, that you can push this more, but then you have to take care also of other aspects. But in case you work at a very low temperature or 0 temperature, you are unlimited. This means that you can navigate in your sample tuning the resolution you need. And my suggestion is the following. Before starting to play this game, please define which is the resolution you need. It's not a washing machine. It's not that you put your sample inside, then you turn the knob to any program. You have in mind something specific. And for example, I would not be able to recognize which kind of part of my sample is this one, but now if I turn my knob increasing resolution, maybe you can better recognize that these are nuclear pores on the surface of the nucleus. And so really you can play a game that is very interesting. And so now we enter in the super resolution. Yeah, we enter in the super resolution. What does it mean? Before This was our conventional imaging. Super resolution means that we are able to see better in some way. Let you know that the term has been introduced by Giuliano Toraldo di Francia, an Italian physicist, late in the 40s. The concept brought by Giuliano is very simple. Giuliano comes from physics, so cannot tell you something like, let's violate physical laws. Would never say this. His statement is, physical laws are there, diffraction limit is there, your cutoff frequency is there, but it's possible that you have some chance for prolonging, for some reasons, the response of your signal in terms of cutoff frequency beyond the cutoff frequency. And if you're able to do this, when you go back, you have an improved spatial resolution. How? Please remember that when we perform this game of sending light to a sample and building an image, we build an image. So we reconstruct an image. We use the information we get in order to have the view to reconstruct an image of the sample. If you have some additional information that can help you in the reconstruction process, this can be helpful for improving the spatial resolution. For example, when you play with a confocal microscope, you are improving your resolution of a factor square root of 2 or something like that. Okay? Are you violating physical laws? Is your microscope exploding sometime because violating physical laws? You can take this risk. I don't think so. And which is the additional information you have when you play this game with a confocal microscope? Is that point by point, you know the position of your investigating beam and of the origin of the signal. If you add this information to the image reconstruction process that uses lenses that are diffraction limited, plus this information, you can improve the resolution, spatial resolution of this factor. Or you can use some other information when you perform some computation on your sample and you use some information of your image formation system, you apply this information to the data you collected, and you try to improve with some processing what's going on. So, for example, you can, before in the three-dimensional space, you could see spheres in this way, and now you see them sharper. Or you can implement, Mats Gustafsson did this. You put on the shoulder of your signal a signal that you know very well, that comes from gratings, moire patterns, or whatever you want, that you insert in your image formation process. You know them very well, and they put on their shoulders the frequencies, unknown frequencies that you couldn't see from your sample, that you can reveal when you reconstruct the image. And so you can move from this to this without violating any physical law. Simply taking advantage of something additional you know about the process of image formation. And so in this instrument, what you have a detector that is made by 25 detectors. And so when you collect your information, you collect an information from the central and from the others. And so this can be a sketch of what's going on. So you have your signal here, and you can collect information from different points at the very same time. You can take advantage of this additional information, and when you reconstruct your image, this is the conventional distribution in space of what's going on. This is the advantage in terms of confocal, and this is the advantage you can get using this additional information, reassigning energy coming from the sample to the point you're interested in. This is what this system makes. Then you can add some other issue and you can transform this in a STED microscope or whatever you want. But the main task, the low cost, comes from the fact that you are exploiting an additional information, like in the presentation given by Alessandro before, of photons that are collected by an array of detectors that have great performances from a lot of aspects. And so what you can get here is an improvement like this one. And if you see in terms of FRC, you have this kind of improvement in terms of excitation power and the resolution calculated using the Fourier-Ring-Correlation. So you can really have a super resolution system without adding too many things except a new detector. This is the system they set up here. So this is a classical image, and this is the image with the SPAD array that is the core of the system. The view comes from here. Now, there is another way you can use for improving resolution. Until now, we have seen some approaches related to some additional information we can collect and use for the reconstruction of the image. What about working on the sample? Well, I like to move to this topic simply because I have the chance to show you my nipotina Irene. Irene has a question. The question is, can we install polymer chains of a swellable material? She has in mind the diapers, I have to confess this, not microscopy, not today. At Boyden, and we are doing the same in our group, tried to answer the very same question, adding some polymer chains to the biological sample. And so, when in your biological sample you have molecules that are at distances closer than the diffraction limit, the idea from Ed Boyden was, at the end, very simple. So you insert fluorescent molecules. You insert a polymer that cross-link the fluorescent molecules. You destroy everything except the polymer and the cross-links. You put this in water. Polymer grows, and the distances between objects that you couldn't see before, you could not distinguish because they were too close to each other, are visible now. One only technical stupid issue is that you have to be prepared to the fact that your sample is growing. So on your stage, it occupies a space that is larger than before. Same stupid issue, but is not when you try to do this. The advantage is that you can use any microscope you have in your lab, already in your lab, any fluorescent microscope, to get super resolution. You don't need any special microscope. Then you can couple this to other instruments, to other confocal, to STED, whatever you want, and you can get improvement. So this is the improvement that you can get in your sample after this kind of process. There are today several ways for making this sort of souffle with your sample, because this is what you're doing. And there is an aspect that we are interested in. So this is what is going on, is growing. Here you can see how the sample is growing by these live images. These are what's going on. This is the normal sample, expanded sample, and the expanded sample seen using super resolution. But then we decided to attack a very interesting point, that is the following. Let's assume that we are isotropic in 3 dimensions. There are science papers, cell papers that tell us about this. So we can trust them. Let's trust them. is there the possibility to have a ruler inside the sample that can tell us how many times we have enlarged our sample? And so we decided to go down to a nanoscale object, that is the nuclear pore, and to try to understand if we can use the nuclear pore and the organization of protein around the nuclear pore to find how many times we were able to enlarge our system. And so this is a possibility. You can have in mind our possibilities. When you play this game within the nuclear membrane, you can also appreciate this channel that probably you know in lamin A, that before we could see only using focused diode beam microscopy. And so you can take advantage of this method at a real low cost, only preparation of your sample. Now we can move to super resolution method. So now, I don't know, I've seen that here that the end is 130, more or less 130. If you survive,
120 maximum.
120 maximum, okay. If you survive, if you want, we can stop anytime. So I wanted to discuss about resolution and this aspect. All the others maybe you know better, except the last part. I will jump on the last part when I have 5 minutes left. Super resolution, you know, maybe you read this paper, and here there is a very nice sentence. I like this sentence. I find poetry in this sentence. It's the first time people is using diffraction barrier is crumbling. La barriera di diffrazione è sgretolata. Is the idea of Giuliano Parodi di Francia. Doesn't matter. We don't mind about the diffraction barrier. We have additional things to put in the image formation process. This is the reason why we get it. And so now the verb is difficult, and we decided to use circumvent by precluding simultaneous emission of adjacent spectral identical fluorophores. This means if you have the ability of controlling fluorescence in your sample, remember Lippico-Schwarz, for example, any method, you can use this advantage for improving in the image formation process the possibility of for improving resolution in the image formation process. And what is nice is that you can apply this to any mechanism. For fluorescence, seems easier, more natural. So you simply have to control switch on and switch off, or different colors, doesn't matter. What you want to do is to exclude when you want from your detector signal of a certain color or of a certain fluorescent molecule. But you can play this game using absorption or non-absorption, scattering, non-scattering, spin up, spin down, if you're able to control them. So you have your diffraction limited signal, point function, and with the Mörner and Betzig approach, and the Lippico-Schwarz protein, so switchable protein, you convince your fluorescent molecules not to send you the signal all together, because you get lost. You are diffraction limited. But one by one, or cluster by cluster, clusters made by emitters that are at distances larger than the diffraction limit. How can you reach this condition? Well, let's assume this scenario. You have your sample filled with your photoswitchable fluorescent protein. You shine a very low dose of photoactivation light, and you have a very poor probability of photoactivating molecules, but you have a very high probability of photoactivating molecules at distances larger than the diffraction limit. If you play this game, you have an additional information that the emitters are single molecules. We will see how we can take advantage of this. And there is another way that is a sort of double confocal. That is STED, is the Stefanel approach. What are you doing now? With the confocal, we get this advantage square root of 2 by the knowledge of the position of the investigating beam and of the origin of the signal. Now, we can improve our knowledge by adding a second beam that tells us from which region we remove the signal. So we know from where the signal is coming and from which region does not come. Putting together this information, we have an improvement in resolution in the image reconstruction process. Okay, so in this case, you have a single molecule. This is emitting, and you can improve your ability in localizing the molecule by a square root of n, where n is the number of photons you are able to collect. It's like if you talk to me, not all together, but one by one or two or three in cluster, and you continue talking. And since I'm sure that people talking to me is only one or two, I can localize them with closed eyes, for example, better if everybody is talking to me. Okay? And the improvement is this one. This means that if you can collect 10,000 photons, that is not a number that you cannot reach with a good fluorescent molecule, you are improving 100 times your localization ability. You repeat this process several times until you get information enough for building your image, and in this case you are able to move from the wide field condition to this condition that is a super resolved condition. With the STED approach, you have this double confocal. Now, what you see here is not true. It's not physically true. So you have a first beam that is the investigating beam, that is diffraction limited. Okay? So you collect all the information coming from the diffraction limited region. Then you shine a second beam, and you can have this microscope for free in this room. You can implement by yourself this process in a very simple way. What can you do for improving your ability in getting contrast, having a look in this room? You can play a game like this. Okay? If you play this game and you shrink, you get a more precise, a better contrast from the region you're watching, and then you scan and you collect the information. If you shrink a lot, the information becomes sharper and sharper. Instead of using hand, that is not so easy with a microscope for the spaces that you have, you use a second beam. It's not true that when I increase the intensity, so the force applied in case of the end, the beam is shrinked, because the beam and the hole at the center of the donut is diffraction limited. So if you shine this to the wall, the extension of the donut is the same. But what matters is the distribution of intensity. If you use more intensity, you have a distribution of intensity that is higher close to the center, and so you have a better ability of switching off or removing from your skin the molecules, okay, point by point, and so you can get this improvement. When you are in the single molecule condition, if you perform well, and so the key of these two methods is your ability in preparing the sample. It's not in the microscope. It's a probe approach. Now, you prepare the sample for the single molecule approach in this way. You make the appropriate steps, and you can collect an image like this one, that is close to this one. But now, if at this step you don't collect, or for some reason the molecule photobleach too fast, and you are not able to collect too many photons, this is what you get. And in case you decide not to label very well your sample, and you are sharp in detection, again, collect something like this. And if your sample is moving, you can collect something like this. This case is not so bad, because during all these last years, people became very, very skilled in tracking single molecules. And so you can put things in the right way again. And so with these two methods, if you decide to write IIT using molecules, what you could see before was this one, and with these two methods, you can read IIT. It's not a matter of reading IIT. The point is that for the first time, I have the chance to count molecules. So I can be more quantitative in terms of my approach to the microscopy image. Now, I like STED, I have to say, in this scenario, because it's very immediate. So this is what I get with the confocal. I switch on the second beam, so I play this game, and I get this immediately. I don't have to switch on, switch off, waiting time, collecting, measuring, reconstructing. I don't need any processing. I can perform some processing, improving, but I don't need. The drawback is that I am influenced by the strength of my hand or the intensity in the second beam. And so if my second beam has a 0 power, I get the confocal image. If I increase to 50 milliwatt, doesn't matter what this number means, I get this, and if I increase, I get this. If I play this game with a DNA origami, with 5 milliwatt, my FRC is this one. When I increase the power, resolution increases, and so the cutoff frequency moves to higher frequencies, and I have the improvement. Unfortunately, Betzig, that is with the other method, is telling us something that is true. Which is the intensity, so watt per square centimeter you need for playing this super resolution game? Well, with the mass Gustafsson, you don't need so many photos. With the photo switching, you need more photons, but not so many. But when you jump to STED, there is an improvement of photons that you need for the second beam. This means that you have to spend a lot of money for your second laser. And if you want to parallelize, it's difficult. So you have to find a way for reducing the strength of the second beam, getting the very same resolution now. One interesting approach is, why not using what I learned from photo switching? Instead of depleting, that is a process that has a very poor probability, and this is the reason why I need a very high intensity, I can use the second beam for photo switching molecules within the donut beam. Cross-section, let's say, is higher, so probability is higher, I need less light, and I can get a game that is similar to the STED one. We can discuss about my position with this approach if you are interested later, because now I have to jump to my last slide. But now, let me bring your attention to what we are really doing. I started telling you that what we are doing is using a double confocal. So one is a donut-shaped beam and the other is a Gaussian beam. And if you use this second beam, at the very beginning we are pointillist painter having this brush, and then we have this brush. And the sharpness of this brush depends on the intensity of the second beam divided by ISAT, that is a property of the molecule I consider. ISAT means that is the answer to this question. Which is the intensity I need for depopulating excited states, so for removing fluorescence, 50% coming from my sample? This is ISAT, is a property of the molecule. This ratio is the ratio giving you the sharpness. But what I'm doing within this donut, I'm canceling fluorescence. This means that I'm perturbing fluorescence that I prime, because the first step is to prime fluorescence. Immediately, I perturb the condition, and I try to have my molecule going to another way, not reaching my detector with a green fluorescence. We can discuss about the process if you're interested, but it's not now the point. When I perturb fluorescence, I give fluorescence an additional chance to go to the ground state. And I know that in a normal case, I have excited state, I am in the excited state, and in order to go to the ground state, I have two ways. One is emitting photons, fluorescent photons. And the other one is going to the ground state in a non-radiative way. This defines the efficiency of the process, or what is called lifetime, so duration of the process. If I give the molecule another possibility for going to the ground state, what does it happen to the lifetime? Since I gave to the molecule another chance, my expectation is that lifetime is shorter. Duration is less because it has another chance. In fact, if I measure what happens, from the center lifetime is this one, and from periphery, if I don't use a very high intensity donut beam, that means I have not the full probability of destroying fluorescence. There are some molecules passing, imagine this, through the donut with their own fluorescence. Their lifetime is shorter. And so now, like children with thunders, I can use counting. When you listen to the thunder and you count, you have an idea of the distance. Well, I shine light, and I count time from the arrival of photons, and I perform a gated acquisition in time. Photons that arrive very early are photons that are very perturbed because lifetime drops down very fast. Photons having the lifetime I expect from that molecules are the photons are perturbed, the ones I'm interested in, coming from the center. And so I can modulate the gating with the power in order to get the same spatial resolution. This is interesting because I can use an additional information for having an improvement. Now, I'm from Genoa. I liked very much this approach introduced by Giuseppe Viccidomini when he was in the Stefano lab, but I was disappointed by the fact that I'm not collecting all the photons I produce. So I pay with the laser for producing photons, and then I don't collect everything. Luca Lanzano comes from Catania. He's not Genoese. But color of his football team are the same, red and blue. Catania and Genoa are the same color. So immediately was in tune with the idea of using all the photons, available photons. And so we decided to have an approach that is not only performing a gated detection, but is classifying and collecting photons according to the time of arrival. If you use this additional information, you can improve resolution because you have an additional information that is the information coming from the classification of the time arrival of photons. In this case, you can also remove background, and so you can improve the contrast. I skip this because it's about fluorescence correlation spectroscopy, but in case you are interested in, for people that perform fluorescence correlation spectroscopy, you can apply this game of classification and of gating in order to reduce your volume of observation and selecting photons by their time of arrival, that with this system that has detectors that are able to collect in a very short temporal window, you can recognize molecules while you are collecting information by their lifetime, so species by species. So you can perform spectroscopy while performing imaging or vice versa. So if you want to know more about STED, you are interested, you can go through these papers, or you can find an old Topolino, Italian version of Mickey Mouse edition, and there was the description of this STED process in this paper. Now I have my last 10 minutes, 5 plus 5. 5 are for label-free. Maybe we can discuss lunchtime about why I'm interested to move to label-free. But with Davide, before we discussed about these liquid phases, in chromatin, so changes in refractive index at the end. We will discuss about this immediately. But now, label-free is related to the fact that in my case, I think, maybe I'm wrong, that for an organization that is at a very high density of compaction, if I insert molecules, the organization could be different. And I'm interested in monitoring the organization with respect to the possibility of opening or closing the sliding door. So I think for this reason, maybe I'm wrong, I think that moving to label-free could be more interesting. And so here you have some fluorescent molecules and their occupation in space, but let's assume that when you have these objects that are 37 kilodalton linked to your instance, not sure, but what I have in mind is that organization of chromatin DNA could change. Not sure. There are good news, so you can have some intrinsic fluorescence that can allow you super resolution, but then there is no continuation for this paper by is the Vadim-Bakan group, or you can use other strategies called nonlinear strategies like second harmonic generation. Sorry for skipping this. I'm interested in a real label-free approach that is called Muller matrix microscopy. I shine light on the sample. I don't mind if there are fluorescent molecules. There are not, but in case they are, I don't mind now. And I do something very, very simple. I try to be an ordered guy. I'm not. So I try to classify the light in terms of its polarization. It's interesting because when you go to the coffee machine, if you insert your coin with the right polarization, you can get coffee. If you try to insert the coin 90 degrees with another polarization, it's not so easy to get a coffee. And so I try to be sharp in this. I control polarization states. In which way? Sorry for this. I use a vector of 4 position. First position is unpolarized light. Second position describes the light polarized horizontal or vertical. Third position, light 40 degrees or minus 40 degrees. But the last position is related to polarization that is circular, so light that is turning this way, right, or left. I describe light in this way. It's appropriate. Then I put myself on the detector side and I try to be ordered in the same way. So I try to select, using a simple analyzer, light unpolarized, horizontal or vertical, 45, circularly right or circularly left, okay? If I see the very same signal, this means that the sample was not affecting the property of light, for some reason that I don't know. But if there is any change, and I wanted to describe in some way this change, since I have a 4-element vector input and a 4-element vector output, I have some reminiscence from the high school, and I know that I need a 16 elements matrix. Each element of this matrix, called Muller matrix, reports about some properties, physical properties of the sample. Everything is really complicated. I have 16 images in one shot. I don't know exactly the origin, but for example, I know something about some of these elements. This element that you can call, I call 1, 2, sorry for this. So I call this one 1, 1 and this 4, 4. But my postdoc from France called in this way. However, this element is related to birefringence. So it's related to a differential way light passes through the object when it's horizontally or vertically polarized. Simple. For all the other elements, I don't know exactly. Some are redundant. Let's think about them. But there is a special case that is this one, 1, 4. Tells me I have 1, 4 if I have some chiralities in my sample. Because chiralities make the sample selective for light that is rotating on the right or light that is rotating on the left. And so in that case, when the sample has no chiralities, no difference. But when there are chiralities, I have this signal. You can use, so I added some because I will skip this. Now, if you think about chromatin and you think about this, and you go back to the 80s, you find a thesis by Carlos Bustamante that implemented in a very brilliant way the Ashkin optical traps. Carlos Bustamante had his thesis on circular intensity differential scattering of chiral molecules. That time, this property was used for detecting different bacteria, different inflammation or whatever. We decided to set up an instrument. Sorry for being fast here, and I want to reach another. Okay, I want to reach this. And we decided that we wanted to use in the 90s this differential information for detecting different ways chromatin is organized. In that case, in solution. Changing the ionic strength, we had the chromatin, a different organization, extracting chromatin in different ways. So potting or cold water swelling, we had a different organizational motifs. Then we stopped for some reasons, and today we decided to build a microscope measuring this element. This is the microscope, more or less, so it's able to measure these elements sensitive to chirality. And we made a very simple experiment. Microspheres against a nucleus containing chromatin DNA. And the signature is 0 for the microspheres, different from 0 from chromatin. Now, I will remove some slides from the next series of slides. But now let me bring to liquidopy and to the way we use this approach. I have again Irene that is asking for which is the future of microscopy. She grew up, so now she has a specific question. My answer is liquidopy, and I will be on liquidopy immediately. Multi-messenger microscopy, that means image scanning microscopy that you will have on this instrument and detector arrays. Label-free. I think that there will be one day that we will be able to remove any contrast mechanism and to understand from the pure interaction of light with the sample what's going on. I don't know when. In order to reach this point, we can use the advantages of having fluorescence in this very sharp way. But I think that this could be a very interesting point. So using Muller matrix, these seeds, phase information. And in terms of fluorescence, is fluorescence dynamics. So exploring the environment with our fluorescent molecules. So you have the fluorescent molecules bound to another molecule. This does not tell anything about the structure of the molecule or what's going on the molecule you are interested in. But if the molecule is changing structure or the environment is changing, this fluorescent molecule that is very close to your molecule of interest is changing properties like lifetime, polarization, photons emitted per time. And if you collect all this information, you can have information about the environment. And so, more information about the molecule you are interested in. For this reason. For this reason, we would like to build this big instrument. And Marco and Simon Luca are very scared because I asked them to be part of this, so inserting everything in the machine. And now I skip the part related to only this part, and I show you only one data about fluorescence and Muller matrix. These are very preliminary results we got. So we decided to perform imaging using Muller matrix for a sample that was also filled by with fluorescent molecules. We need a reference. So, and this is DAPI, not a very nice image. And this is the signature of region of chromatin related to their compaction and to the average compaction that we have in those regions. So this is a very first starting point in mixing these two applications. Liquidopy. All the methods you have seen before presented in a different way, like drops, it doesn't matter this, but bringing now your attention to this. When you have a look to this image, I'm not sure you can learn something more in terms of anatomy. You can like this picture or not. When you have a different way of representing information, like in this case, like in the case of clay, maybe you can be attracted by some region that don't fit exactly the real world, but can bring you to a region of the image with some attention, and then you can go there studying better what's going on. Liquidopy is a way, liquid comes from, I can take this slide. Liquid comes from the idea of Zygmunt Bauman or liquid society, the individualities. Tunable is resolution tunable. Microscopy is microscopy. Let me give you I take only 1 minute to give you this example in order to let you understand what I have in mind by using classification of my images and an approach that is a deep learning approach. Let's assume this now. Forget microscopy. Think about you. You go to the doctor with some symptoms. And the medical doctor tells you that you need some investigation. So let's say X-ray, PET, and thermography. You get them, you go to the expert. Each of them, and this is my point with the liquidopy, a little bit biased, tells you the diagnosis with this specific approach. Then you go back to the doctor, and there is something happens. My point is that I build an instrument. Let's assume diagnostic now. You go to this instrument. You tell the instrument in a verbal way which are your symptoms. You enter in this machine able to perform all these investigations together. The system, following your verbal description, getting information from literature, and the story of your sample in your question, decides which are the best image contrast mechanism that you need for solving your problem. But at the very same time, while performing this kind of imaging that is classical, so can be super resolution, can be phase contrast, so the methods PET, X-ray, or whatever, produces, in this case, a fourth image. Point by point, in this image, are reported the data coming from all the investigation method, mixed in a way that I would like is a way not biased by an experience made by the single expert in PET, in X-ray, or in thermography. At the end, with this image, you go to the doctor, and the doctor tells you, now I clearly understand what you have. Hey, guy, you are without legs and nose. Well, no, I have. The reason is that the doctor is not able to read this image, sees something that he had in mind but he cannot find there, or she cannot find there, that can be attracted by some region, and now focusing on this region and going back to the so-called, let's say, classical image, can have a different approach to the data acquired, less biased than before. Why doing this? Because I think that we are performing imaging in fluorescence since the 60s, and we don't understand anything of what's going on, of so many things in maybe we are biased, there is a mistake, and so the possibility of a new approach maybe can open a new way for interpreting images. In this case, this is an associative memory approach that tries to insert some chaos in the image in order to find regions related to organization. Probably machine learning can help for a stage that is, on one side, machine learning, so all the part related to the knowledge and the way knowledge can be used, and then deep learning that is a way for revising parameters for taking a decision based on the processing that is going on. That is what I need. I don't want something biased since the beginning. Okay, this doesn't matter this, but let me give you this last slide. Liquidopy, this is my idea. This is Hugo Pratt idea of the real world. Could provide the opportunity to see things, to change point of view, abandoning the obsession of representing the real world we have in mind when we form an image. I think that if you think what you are doing when you start approaching your microscope, most of the times you have in mind the image that you want to see. Let's try to remove this. We are not able. It's difficult. Like poker players, they use dark glasses because the intention is something that you cannot remove. But if a machine is able to perform this for us, this could be maybe helpful for interpreting the real world under a different perspective. Victims for this are these guys. Sorry. And I thank you that we are victims today for this lecture, and I thank you for your attention today. So if you have questions later, after